Okay, so let's continue with transition elements. As we said, right, the 10 groups in between group 2 and 3 in the periodic table are all transition elements. They are also known as transition metals because all are going to have metallic properties. They are having some properties similar to normal metals and some properties will be different. And we just discussed some of the properties. They are very hard and strong metals, which is unlike group 1 and 2 because they were soft. They are good conductor of heat and electricity, just like group 1 2 metals. They have very high melting and boiling points, high density as well, unlike group 1, because group 1 was having low melting points and low density. We can have one comparison, one example as well. Melting point of titanium from the transition metal is more than 1600, but for the potassium from group 1, it is only 63. So there is a big gap, big difference in the melting point values. Then we also say them transition metals because they all make some colored compounds. Group 1, when we said they are going to make the aqueous hydroxides, we did not say they are going to be colored. Group 1, Group 2, they are not colored. They don't make the colored compounds. But this is the property of transition metals only, that they are going to be colored. So this is something different from others. They have some physical properties different as well, but the color is also different. Okay, it's also physical property, but it's different. So colored compounds are going to form. So this is only for transition metals. Then other differences, more than one oxidation state. So here, first of all, I will tell you what is oxidation state and oxidation number and how we can tell it has more than one oxidation state. Oxidation state means what charge they can have after losing electron, plus charge. Because they're metals, they're definitely going to have the positive charge by loss of electron. So oxidation state means when they're going to lose electrons, getting the charge, how much charge they can have. If they have +1 charge or maybe +2 charge, we can say this is known as oxidation number. +1 means it has oxidation number 1. +2 means it has oxidation number 2. Okay. More than one oxidation state means now they can lose electron in more than two different ways. Like if we take iron as an example, iron can make Fe+2 as well. Iron can make Fe+3 as well. +2 means loss of 2 electrons, +3 means loss of 3 electrons. In group 1, we said all are losing just one electron. So it means they were having just one oxidation state, one oxidation number only. But the transition metals have this property, they have more than one oxidation states. So let's see in more detail this oxidation state, then we'll come back to this. So here is a little explanation of the oxidation state. More than one oxidation number. Why they can lose the different number of electrons depending on their environment. Environment means what is the other reactant. If iron is in one type of the reactant, it will lose 2 electrons and it will make +2, means oxidation number is +2. 2 loss of electron. If it can lose 3 electron, maybe now there is another reactant which is helping the iron to lose 3 electron. Okay, then it will lose 3 electron, getting the +3 charge. So oxidation number is going to be +3 now. So they have property that iron can have maybe +2 charge, maybe +3 charge, depending upon the condition, depending upon the other reactants and the chemical environment. Okay, so depending upon this, we can see some other examples as well. It's not just two types of the oxidation, maybe more than two. Let's say if we talk about titanium here, titanium can lose 3 electrons and make +3. Titanium has just one oxidation state, but still that one oxidation state has a color, purple color. So color is the property of transition as well. If we talk about vanadium, V, it can lose maybe 2 electron +2, 3 electron +3, 4 electron +4, and 5 electron +5. And when the oxidation number is different, the color is also different. Purple, green, blue, yellow. So different color solutions will produce depending upon how many electrons they're losing here. Yes, Jude.
Yes, miss. So my question is that if they can lose, multiple number of electrons, it doesn't
Hmm.
need to be a specific number. So don't they need to reach a specific, number of electrons in the valence shell? So how
Yes,
can this
definitely.
happen with multiple numbers?
Definitely, it is going to happen depending upon the other reactant. If other reactants want 3 electrons, they will lose 3 electrons. Make the bonding accordingly. If the other reactant needs 5 electrons, they will lose 5 and make the bonding accordingly. They will also satisfy the valence shell as well. Okay, so they will react according to the other reactant or chemical environment, and then they will satisfy their outer shell as well. Okay, yes, Varif.
This, to add into this question,
Hmm.
I didn't get, like, if you use five, they will be stable?
No, no, if they're losing 5, it means their inner is going to still have 8. Outer 5 is going to be lost.
Mm.
Okay, or maybe when they're losing 5, maybe they're sharing it somehow that the outer electron still will become, the outer shell valence shell will still become stable. So it depends upon their environment now.
Okay.
That the other reactant is from the maybe group 5, maybe group 7, maybe group 2. What is the other reactant here? Other reactant will decide how many they can lose. And overall at the end, they have to be stable. They need to complete their octet to become stable at the end. Okay? Yes, Mariam.
Yes, so it can lose 7 electrons.
Yes, not vanadium. Vanadium is not losing 7. Vanadium has only 4 possibilities, plus 2, plus 3,
No,
plus 4, plus.
manganese.
Okay, manganese. Manganese has 2 possibilities, plus 2 and plus 7 only. So they have specific possibilities only, and both have different color, light pink and dark pink. Chromium has 3 possibilities only, plus 2, plus 3, and plus 6. Iron has 2 possibilities, plus 2 is green, plus 3 is brown in color. Cobalt has 1 possibility, plus 2. Nickel has 1 possibility, plus 2 with green color. Copper has 1 possibility, plus 2 with light, you can say violet or blue color. Okay, so like this, they have different possibilities. So there is no trend in transition that they may have how many oxidation states, how we can remember, like we need to remember maybe. In the exam, they will not ask you how many oxidation states are there. They will ask you the question in different way because every transition metal has a different trend. Some has one possibility, some has two, three, four, five. Different number of possibilities are there to lose electron. Okay, there is no proper trend in it. Yes, Samreen.
So miss, in the exam we can be asked, like, for example, chromium. It is
Hmm.
like it is losing 6 electrons. So what is the color of it when it loses 6 electrons?
Yeah. So what they can ask? Let's say, let me give you one simple exam question about Fe. What we just said. Fe can have maybe plus 2, maybe plus 3. I'm writing two formulas here, and you will tell me in which formula which oxidation state is present. Okay. We have, let's say, FeCl2, iron chloride. We have FeCl3, and other iron chloride. So what is the oxidation state of iron in FeCl2 and in FeCl3?
Miss, wouldn't FeCl2 Fe plus 2 and like FeCl3 Fe plus 3?
Yes, how you got it?
Because like miss, like the chlorine,
Hmm.
it's need to be balanced, right? So for
Hmm.
balance it, we need 3 and 2.
Right. Chlorine is from group 7. We said group 7 has a fixed oxidation state. Like they can gain one electron having negative one charge. That's it. No change in chlorine. Every chlorine is going to be negative one. 2 chlorine means they are going to be total minus 2. To make overall charge stable, iron should be plus 2. So here the iron is Fe plus 2 iron. Here 3 chlorines are going to have minus 1 charge means total minus 3 charge. Minus 3 charge for 3 chlorines, it means here the iron has plus 3 charge. So this is one of the example. Here the iron plus 2 is participating in the reaction. Here iron plus 3 is participating in the reaction. Depending upon condition. Here 2 chlorines were available. Here 3 chlorines are available. So they are changing the oxidation number, losing different number of electrons depending upon condition, availability of other reactant. Okay, depending upon the chemical environment. So like this, they can give you these two formulas in the exam and ask you to find the oxidation state of iron. And maybe they can ask you by giving some colors and identify what is going to be the color for this iron compound and this iron compound. Iron compound with +2 is going to have the color green. Iron with +3 is going to have the color brown. Or maybe they can ask you, are they both having same color or different? Definitely they will have different color because of different oxidation state. Okay?
So do you have to memorize the colors
No. No need to memorize these colors. No need to memorize these oxidation states. Okay, just memorize. They have more than one oxidation state sometimes that from formula you can easily get. Okay, no need to memorize this whole thing. Just an idea how we can find oxidation state, and difference in oxidation state means different colors will be there. I hope this is clear to everyone. Any question till here?
Yes.
Okay, let's move forward then. We talked about the oxidation state. Then let's see some other properties of the transition metals which are different. That is the reason we don't have group 1 and 2 in transition, because group 1 and 2 has a fixed number. Group 1 can lose 1 electron plus 1. Group 2 can lose 2 electron plus 2. No change in oxidation. Plus, another property is group 1 and 2 does not have colors. They're not colored compounds. So they're different from transition. So they're in separate groups. Okay. Transition metals, because they have colors, because of their colors, they have some properties. They are responsible for pigments in many paints. In many paints, to give different color in paint, we add transition metals in small quantity. Color of gemstones. You use some stones for your rings, right? Those have transition metals inside to give them specific color. Some rocks which are colored, they are colored because of some transition metals present inside. Okay, so these are properties depending, uses depending upon their colors. Yes, Mariam, any question? Mariam or
Yes,
Mama
miss.
also. Yes, Mariam, your question first.
Actually, miss, for the second page, you wrote that Fe Cl3. Yes.
Right.
Uh, if FCl is already having a -3 charge. So the -3 charge and the positive 3 charge will cancel each other, yes?
Yes. Overall, they don't have any charge because +3 -3 cancel out. FeCl3 is neutral. That's what we said when we wrote the formulas. We said that overall negative positive should cancel out and overall formula is going to be neutral. So every coloring is -1, overall -3. To cancel the -3, we need +3 from iron. Same way to cancel the -2 here, we need +2 from the iron. Okay? Yes, Mama, your question?
Miss, in general, where do we use these transitional metals?
Yes, we use them in paints. We use them, maybe you have seen different color of the glass material. Glass for the windows, glasses that we use in our houses as well sometimes. The colors, most of the time, the dyes we add contain some transition metal. So we can give color to the glass material, we can give color to the stones, to the rocks, so to the paints. To give the colors, we can add a small quantity of transition metal depending upon what color from here we want and what oxidation state we need. Okay. Okay, let me tell you one thing here. Few days ago, one of you asked that sometime we write a Roman number in the bracket, in the formula. What does mean by that number? Now you will be able to identify that number. Okay, FeCl2, FeCl3, both have the same name, iron chloride. If I say you, okay, you have iron chloride, you can do the reaction. Which iron chloride? Let's say I'm telling you we have iron chloride provided for any reaction. So you will be confused if the iron chloride FeCl2 you have or iron chloride FeCl3 you have. Now to make a difference, we can add a number in the formula. For FeCl2, we can say it is iron bracket 2 in the Roman number chloride. So this 2 in the bracket is telling you the oxidation state of this iron. It's +2. 2 oxidation state is there. For this FeCl3, we can name it as iron 3 chloride. Both are iron chloride, but iron 2 chloride means its oxidation state for iron is +2. So 2 lines are there, number 2 is there. For iron 3 chloride, we can say iron bracket 3 chloride. It is important. Why? Because if we just write iron chloride, we will not be able to identify FeCl2 or FeCl3, which one we have to use. Okay? Yes, Samri.
Miss, like, what is the difference between oxidation number and oxidation state?
Oxidation state means any compound having some charge. Oxidation number means how much charge is there. Okay?
Mm,
So it has oxidation state means may have some charge, right? But how much charge? +2, +3. That is the oxidation number. Okay? So oxidation
for
number is
state,
telling what oxidation state is there, what specific number is there. Okay?
so miss
Hmm.
between them.
Any other
Like
question?
oxidation and oxidation state has no difference between them, right?
Yeah, oxidation state or number is same thing. Oxidation state means it has some charge on it, plus charge. And oxidation number means how much charge is there, +2, +3, +7, like this.
Oh, and
Okay.
miss, like,
Hmm.
for the examples, we don't have to learn the colors. So, like, we just have to know that, like, they
Hmm.
have different oxidation number and
Yes.
states.
No need to learn it. Maybe they can ask you by giving this formula to see that iron oxidation state or number is same in both or no. Maybe they can give you this type of the name, that why we have this 2 and 3 numbers in the bracket. They are telling you about oxidation number of this iron is +2, this iron is +3. So it means iron is present in 2 different oxidation states. Okay.
miss.
So like this we can identify. We are not writing this kind of the bracket for group 1 or 2 because they don't have 2 different numbers. They just have one oxidation state. So no need of this bracket for them. But there is a need of this bracket for transition metals because they may have more than one oxidation state. So we have to tell what oxidation number is there. Okay.
Okay.
Okay. Let's move back to some other properties. Transition metals, we have seen their uses. They are also used as catalyst. Most of them are important because they help in speeding up the reaction. So we use them as a catalyst. One use of transition metal as a catalyst is in catalytic converter. We have a separate chapter on the catalytic converter, so I will not go to the long discussion here, but I will give you a little summary. Catalytic converter is something that we have inside our cars. This kind of the apparatus in the car, what it is going to do when we use the fuel in the car, as we discussed today, that fuels combustion or burning is going to produce some dangerous gases at the end, the greenhouse gases, right? So if we don't use this catalytic converter, what will happen? The car is going to produce the fuel, and that fuel can directly go to the air, to the atmosphere, and add and do global warming, greenhouse gases. Greenhouse effect will be there. So what we can do? We can put this catalytic converter in the car. So dangerous gases or the greenhouse gases can enter the catalytic converter and they will come out in the form of safe gases. Again, harmful gases will enter this catalytic converter. This is inside the car. Before the gases come to the environment, to the air, they have to pass from this catalytic converter. So harmful gases are entering the catalytic converter and then they are leaving from the catalytic converter as safe gas. So inside the catalytic converter, we are using some catalyst made from transition metals, which are helping these harmful gases to change into safe gases. How they are changing, what reactions are happening, what will be the chemical equations, everything we are going to study in a separate chapter. So we are not going to do the detailed discussion of this catalytic converter here, just an idea that here these transition metals are very useful, which are helping the harmful gases to change into less harmful or safe gases, and then they can release into the atmosphere. Okay, so harmful gases examples are such as the nitrous oxides and carbon monoxide. They are produced from the car in the form of when the fuel is going to burn. If they directly add into the air, they will be very dangerous. So catalytic converter will convert them into less harmful gases. So which catalyst we can use? Platinum and rhodium. Both are transition metals. They are useful in catalytic converter, helping the reaction to proceed and making the reaction faster so that they can convert into safe gases. Okay, let's move to some other application. One thing very important, scandium and zinc. We have scandium over here and we have zinc over here. They both are right now, you can see blue. You can see they're part of the transition group. Transition 10 groups, they're part of the transition groups. But still, these two are not transition metals. This is also one important exam question. They can ask you, scandium and zinc, is they transition or no? You will come back to the periodic table, you will see, okay, they are in the 10 groups, so yes, they are transition. No. Why they are in the transition block, but still they are not transition metals? It has a reason. Number one, they just make one oxidation state. Okay, that is not a big deal because we have titanium having only one oxidation state. We have cobalt having one oxidation state. What's the problem? The problem is they have one oxidation state and they do not show any color. They do not form colored compounds. Transition metals have the condition they should make colored compounds. So if these two are not making colored compounds, it means they are not transition metals. They are just metals. Okay, yes, Varif.
Miss, so why do we count them from the transition metals?
We are just we are just saying that they are in the transition block, but not part of the transition metals. Okay, they are in
Oh, okay.
those 10 groups of the transition, but still they are no transition metals. We'll exclude these two. Okay, yes. Any other question? Yes, Mariam.
So Miss يعني they are in the transition metals but not يعني
Yeah, they
not
are in
considered as
they are in those 10 groups of transition metal, but still they are not transition. They're present over there for just like hydrogen. Hydrogen is present in the group 1, but hydrogen is not group 1 metal. Hydrogen is non-metal. We will not talk hydrogen when we are talking about metals. We will exclude hydrogen from the discussion, but still it is in group 1. Same way, these are in the transition block, but not transition metals. And the reason is they just have one oxidation state, okay, and they are not making colored compounds. So they too are excluded from the transition metals. Okay. Okay. Some uses of the transition metals, some of them we have already discussed. They can be used as a catalyst. And okay, why we are using them as a catalyst, I will just tell a little explanation over here. Then other properties are we can even use them in medicine and surgical applications as well, because they are very important when we want to replace the joints and limb. So they have some important uses over there. No detail needed for you. Just medicine and surgical applications we have. And then they're also used to make dyes, paints, and stained glass, and then jewelry as well, because they have different colors. So they are important and useful whenever we need something colorful. Okay. Yes, Mariam.
Miss but the يعني so the see the scandium and zinc are not
Transition, yes.
but why and CD are considered
No. The reason is because they're not making colored compounds. We said all the transition metals have the property they are colored.
I mean
Okay.
the elements below them.
The element, which one again?
The elements below them, they are considered or
Yes,
also
yes,
not
they are
considered?
transition. Element below them, they all are transition. Just scandium and zinc. Okay,
Okay.
two only, not the whole block, whole group under it. No, only scandium and zinc. They are no transition.
Mm,
Okay.
okay.
Okay, here I will tell a little discussion about catalyst and then we will end the lesson. So catalyst, why they are behaving as a catalyst. Any idea you know what is a catalyst? Uh, is the catalyst participating in the reaction or what the catalyst basically do in any reaction? Yes, Samreen.
Miss catalyst is usually is like on top of the arrow because it is
Right.
just used of the reaction. It doesn't participate in the reaction.
It does not participate in the reaction, so we don't write it in the equation. Actually, we write it above the arrow in the equation. Okay. Anything else anyone knows about catalyst? It is not participating in the reaction, then what it is doing?
Miss, it's speeding up the reaction.
Yeah,
It speeds up the reaction,
such
not
as
participate in the reaction, so we don't write it in the reactant form. So now we will upgrade this definition. Catalyst basically participate in the reaction, but how they are participating, it matters. They will participate in the reaction. They will change their form to something else and then change back to original form. At the end, we will have something original, unchanged. So we say it in the short words, no change in the structure, no participation of the catalyst in the reaction. But in reality, now in IGCSE syllabus, we'll see catalyst is participating in the reaction. But at the end, it will remain again in the original form. How? Let's say I'm using Fe2 positive as a catalyst. Okay. As I said, it will participate in the reaction. Let's say you have a reaction having two steps. In the step 1, this Fe2 positive will react with something, lose electron and changes to Fe plus 3. I'm not writing full equation, just catalyst. I'm focusing on catalyst only. Fe plus 2 can lose electron and go to Fe plus 3. So we added Fe plus 2. If it is catalyst not participating in the reaction, it should not change to Fe plus 3. If it is changing to Fe plus 3, it means it is participating in the reaction now. Okay, what will happen after that? In the final step, in step 2, this electron will go and whatever it has to do, it will do and come back. Now, this Fe plus 3 at the end, in final step, will again take this electron and go back to Fe plus 2. So what we can say, Fe plus 2 was the catalyst at the start. At the end of the reaction, it is again Fe plus 2. No change. So in short words, we can say catalyst is not participating in the reaction, but actually it is participating in the reaction. It is changing into something else. Then it is giving out the electrons maybe. Those electrons can go and help in reaction. At the end, they can come back and Fe plus 3 will take the electrons again and go back to Fe2. So we'll get whatever we added at the start, we'll get the same thing at the end of the reaction. So we can say overall catalyst is not participating, not doing anything. It is going to remain the same and only speeding up the reaction. But it is participating and then coming back to original form again. Okay? Yes, Umama.
Miss, we should, so for the definition, we would say that it is participating, but it will come back. This is the final definition, right?
This is the definition for only those catalysts which are transition elements. Why?
Okay.
Because
Why?
transition elements have the ability to have different oxidation states. So their catalysts are participating in the reaction. Okay? They can change the oxidation state, participate in the reaction, then they can change the state again, go back to original form. So transition elements catalysts are participating in the reaction because they have the ability to interchange between the oxidation states, plus 2 to plus 3 back to plus 2. This is one example only. We have many examples like this. Okay, so they can easily give out the electron, they can again gain the electron and go back to original form. So when we have transition metal catalysts, they can participate in the reaction because of the difference in oxidation states. Yes, Maria.
Miss, why it can't be any why if E2 positive 2, why can't it directly go without gaining one electron to be without changing to Fe plus 3 and gaining more electron to be Fe2 plus 2 again?
No. Fe plus 2 means loss of 2 electrons. First, it has to remove 1 and get plus 3 charge. We don't need plus 3 at the end. We need something original at the end. Plus 2 again. To get plus 2 again, this Fe plus 3 again need to take the electron back. Okay, so that it will become plus 2. Plus 3 means 3 loss of electron. It is gaining 1 back. So plus 2 only. Means 2 loss of electron. So to change this into original form, it will again gain the electron. And catalyst is
So
something that will remain unchanged at the end of the reaction. Means at the end, we need something original back. Only then it is a catalyst. So transition metal catalysts can participate in the reaction, change their oxidation state, go back to the original state, and then they will end the reaction. Okay? And that's
so
all
it
for
will lose an electron and gain it again.
yeah. So it will lose and then take again. Go back to the original form. Okay?
Mhm.
Any other question here?
No, miss.
Okay,
No.
that's the end of the lesson. Have a nice day. See you later.